Hello and welcome to this new episode of Commodore 64 Games Reverse Engineering. I'm going to be reverse engineering a complete game and providing all of the source code so that you can actually use this source code to then create your other games. So I'm going to be looking at the Shoot 'em Up Construction Kit. The Shoot 'em Up Construction Kit was released in 1987 but also re-released several times after that. I think I had the version that was labelled as being developed by Sensible Software and published by Outlaw, which was at the time part of Palace Software. When I bought this title, I think it came in quite a large black plastic clamshell case and had a Shoot 'em Up construction kit with a couple of spacecraft on the front and the Outlaw logo, and includes 4 free games. With this construction kit, it allows you to edit sprites and objects. So for example, define the animation frames. It also allows you to define enemy bullets and explosions and all sorts of frames and how they move. So you have directional frames like the player ship here, or you have sequences of frames which repeat. It allows you to edit the characters for the background, the blocks for backgrounds as well. So these blocks are 5x5 character blocks, and I think you have 128 of these, up to 128 of them. And of course you can arrange the blocks in vertically scrolling maps. There is a horizontally scrolling variant of the Shoot 'em Up construction kit, which I never had back in the day, but I found out that it actually exists. You can edit sound effects, you can set the player limitations, so you can say, for example, set how many players you have at the beginning of the game, whether or not the second player uses the other animation frames, when you get new lives. You can also set out how the levels work as well, so you can say, for example, have scrolling parts of levels, you can have static screens that stay there for a certain amount of time, you can have push scrolling or forced scrolling. You can choose whether or not they redraw or continue from what's on the screen, and you choose the level graphics from ranges within the map. So if you have a static screen, then you just choose your starting position, but if you have a forced scroll or push scrolling screen, then you choose the start and end position. You can also edit the character set and the message for the title screen, and also the color cycling effect. You can test the game with or without a cheat mode, and here this is one of the example games that was included with the Shoot 'em Up construction kit. You can see it's got full screen scroll, it's got sprites in the border for the score, and it's not too bad. One of the things that some people don't tend to like about the Shoot 'em Up construction kit games is that everything is oriented around this 5x5 character block for the map. To be honest, the colouring of the blocks is a little bit limited. The sound effects always seem to sound the same. It's difficult to make them look a lot different, but you can change quite a lot of the graphics. The thing is that this version of the Shoot 'em Up construction kit suffers from quite a lot of slowdown and sprite flickering, and also the flickering of the score palette as well that you can see here, which is one of the things that prompted me to actually reverse engineer this back in the day. And of course you can save and load the individual data, but you can also save all of the data and save a finished game. Now, back in the day when I first got this, saving a finished game was almost like black magic to me, because it allows you to save the game to disk but also to tape, and it's great. It actually writes a lovely little auto-running tape turbo loader. So I thought that this was a fantastic addition. Obviously it's a logical addition to a games editor. You want to be able to export your games, but having the whole editor all in memory all at the same time, and also having enough memory available to have, to be honest, quite a large scrolling map with enemy attack waves and sprite animations and sound effects was, actually a pretty good feat. So here you can see me creating an example tape file. We can see that the initial part of the full game save is actually using what looks like the kernel load, and it's going through an indirected jump at 3 to 8, which is going to be the stop key vector check, right? Almost certainly, there we go, the stop vector, which checks the stop key being pressed during the kernel save or load. The kernel file routines, basically. So this is what changes the border color for this, but then once the kernel has saved its thing, then it changes to a screen on turbo save, which then shows you the number of blocks that it's saving. The thing is that, as I found out later on when I was poking around in the completed game versions that were saved, I've actually found that the full editor is also available. So actually pretty much any SEUCK game, unless it has had all of this extra code stripped out, you can actually reset the Commodore 64 and jump back into the editor by using a particular poke or a particular sys or a combination of both. This meant that if you weren't careful, then people could just take your games and then edit them further and then re-release them. You could, of course, clear out the superfluous editor code and the editor graphics, and then that would make it a lot more difficult to resurrect your game within the SEUCK editor, but you could still do it if you knew which data had been cleared and to restore that data, of course. So we can see once we load the example game from the tape that was written, we could see that it uses the auto run method of jumping through that vector at 32C. Again, of course, the tape header buffer is actually empty. It contains 20, but it loads, as you can see, it loads a little bit of code up at the start of screen memory there. That's why we can see a whole bunch of characters up at the top of the screen there. So anyway, this was a nice little auto run tape turbo loader that was saved from the editor. I just thought back in the day that was fantastic, and it actually allowed me to experiment quite a lot with finding out how to create my own tape turbo loaders way back in the day, because I had a working example of something that would actually save and then load back again that I could interrogate and have a look at and to reverse engineer. So we can see here it's just a simple loader, right? There is a check there for a checksum, and if it fails the checksum check, it goes back and it seems to try reloading the data, I think it is. Or maybe it's just looking for the end address or something like that. That might also be it. It doesn't actually look like it was a checksum check, just the end of a data to load address by the looks of it. Anyway, so we'll skip ahead, I think, here, because otherwise it'll take far too long to load. So we can see that it's just got a whole bunch of data. If we keep on looking through the memory that was loaded, we can see here that there's some code which starts the game, and here is the game that was saved out. So it's a standalone game, it just runs. If you press the restore key, it quits back and it exits back to the title screen. If we have a look through the memory, there's a whole bunch of extra code in here. There we go. You can see some text messages that relate to the editor functionality. Sprites, background objects, sound effects, attack waves, etc., etc. There's a press play, recording message, searching message, etc., etc. Blah blah blah, lots and lots. Oh, rise, fall, wave, attack, decay, sustain, release, sound effects. So there is a lot of editor-related data in here. So that was a very quick overview about what the Shoot 'em Up construction kit actually allowed you to do. There's a wide variety of games out there, lots of different graphical styles. To be honest, I don't think the capabilities of the Shoot 'em Up construction kit are so limited that the games all appear identical. I think there are certainly different graphical styles out there. So here is actually the poke that you can do, and then the sys statement which runs the editor or restarts the game. So there is a poke that you can do which lets you press space and then go back to the editor from inside the game. So once that finishes loading, I can just use the machine code monitor to do that poke, and then to see if that works. Don't even need to reset the Commodore 64 if you have access to a decent machine code monitor in an emulator, or back in the day you would have used a freezer cartridge, of course, like the Action Replay or the Expert cartridge. So there's the title screen. The restore key doesn't let me go back, pressing space doesn't let me go back to the editor right now because I haven't done the poke, so let's put the poke in. 16964, and then put a 1 in there, press space, and there we go. So as you can see, even though it's a save finished game, we can see that it actually contains all of the editor code still. And then you can edit it, edit graphics, whatever. I remember that sys statement now, which is 24576. I remember now it actually just triggered a memory when I was looking at that page, and that just basically starts the editor without you even needing to worry about entering a poke beforehand, I think. This is also one of the example games that was included with SEUCK, and it's a push scrolling. It's a little bit like Commando, or vertically scrolling, shoot the enemies type thing. But because it's push scrolling, it actually demonstrates quite an annoying bug that I really didn't like back in the day. But it's even more annoying now, is that when you scroll the screen, the sprites are disconnected by a frame. So the sprite Y position seems to move up and down as the screen stops and starts scrolling. So the foot, say for example, of that character there is not aligned with the background. The whole actual graphics aren't aligned with the background from the sprite's point of view. So the sprite seems to bounce up and down every time the screen starts and stops scrolling, which is, to be honest, a little bit untidy. The game does use a multiplexer, but the multiplexer is not that great. I mean, it's passable, I would say, but it does have that flickering and slowdown image. The rationale for doing this full reverse engineering is to reduce the slowdown and flicker that you can see in SEUCK games, remove the sprite-to-sprite background scroll start stop wobble issue, and also remove the wasted memory because the editor is mostly still present in the exported completed final games. Also, it's a good learning exercise on how to reverse engineer something and then to create code which reproduces that behavior as well. So I'm going to be looking at how to find the characters, blocks, and maps, and the colors for the blocks used. Then I'm going to be looking at sprites and animations and firing of enemies and the player obviously as well. The attack waves, how those work. The score panel, graphics. Now there are two aspects to the attack waves. There's the trigger point inside the map and actually the movement itself. And then of course there are the sound effects and the title screen. This is the important thing to note, is that since we have an editor, we can change small pieces of data to locate their position in the all data file. And we can locate that data by doing a binary difference between one file and the next, and remembering what we have changed. To easily access the all data file, I'm going to be starting Vice in a special way from within this directory. And I'm going to be telling Vice that I want to enable virtual device traps for the disk and disable true drive emulation, and also to save individual files rather than write to a disk image. What this will let me do is that it will allow me to save files in SEUCK and then to see individual files on my PC's filing system, so that then I can, without needing to extract them from a disk image, I can then just load those files and compare them. When I'm working out the offset inside the file for all these pieces of data, I actually want to make sure that I'm using a consistent reference point. So this is why I'm using the save all data file all the time. I don't want to save out the individual sprites, background objects, SFX, attack waves, and so on and so forth. I actually noticed sometimes that when I was working on a game way back in the day, if I saved out all of the individual pieces and then loaded them back in again, sometimes it would be missing information. I found that the only really reliable way of getting all of my state saved was to save all data. And basically what it does is that it practically saves all of data. It saves everything from almost the beginning of memory to the end of memory. So I saved out my base reference version, which had no changes at all from the blank SEUCK game. The blank SEUCK game basically has this: it's blank character set with 1 pixel set in the first character. The whole level is filled with the same block of the same repeated pixels. There's a very simple bullet character, a bullet sprite, and there's a very simple player sprite, and that's basically it. All of the other animations and everything else are empty. So what I'm doing is that I'm actually using the editor now to edit the first character, character number 0, to add a whole bunch of red pixel colors, and then I'm editing the last character. So you can edit characters from 0 to 253. I don't know why the last 2 characters are not actually editable, but okay, never mind. And then once I edited just the characters, just the start and just the first and the last character, then I can save all data with a suitable file name indicating what was changed. In this case, it's the characters. And then we whiz ahead with warp mode and with the virtual device traps turned on. It's actually quite quick. So I'm changing the colors now. I'm changing the background color. I'm changing multicolor 1, I'm changing multicolor 2, and then I will be changing the block color as well, because I want to find where these pieces of information are stored in the file, right? The way to do this kind of reverse engineering is to be very methodical about it. You change one small thing, or maybe a couple of small things, and then you look for the data being changed. You can, for example, look at data being changed in a file across multiple files and then do a binary difference. That's one way. You could, of course, change the data in the memory and then use the monitor to save the whole of memory as a snapshot. You could do that too, but then your base frame of reference for the changes that you're making for the data that you're looking for is going to be from memory dumps, which is a little bit less accessible and slightly less easy for people to produce, rather than producing a full file, which is from the save all data option. So this is why I'm choosing to map it back to the save all data file, because I know that that's a consistent reference point. I know that the same code saves all the data, and I know that the state is going to be consistent, so I'm trying to reduce as much as possible any unexpected changes. So here what I'm doing is that I'm editing the blocks by introducing new characters into a few subsequent blocks. So there are, I think, 128 maximum blocks, 0 to 127 in other words. So I'm just editing the first couple of starting blocks, and then I'm hoping that the blocks are stored in contiguous blocks in memory, of course, from start to end, and I'm just editing the last block now, block number 127, and I'm just using character number 3 to edit what that block looks like. I'm editing the full range from the top left to the bottom right of the block. One, I'm kind of assuming that the characters in the block are laid out in that format. It makes sense if they are. I know they are. I've done this work before. I'm just going through how to reverse engineer. All of the code is complete already, of course, and you can actually download the code already and use it in your own projects. No problem at all there. But these series of videos are going to go into a little bit of the more detail in the actual steps that I did way back in the day to reverse engineer it. So you can see my thought processes and you can see how the data is discovered. So now editing the map, of course, the map is actually quite large. I forget exactly the coordinate base that it's using, but we can see here that there are 8 blocks horizontally, and because the whole map is filled with the same blocks at the moment, then it's difficult to count. But I think it must be 100 blocks at least tall, vertically scrolling. So there's the last row, there's the bottom of the virtually scrolled map, and then I'm trying to zoom all the way to the top. It's going to take quite some time, There we go. I haven't reached it yet because I painted in a whole row, you see, and then it scrolled off the bottom as I moved up. I'm also warping ahead in the emulator, which, to be honest, helps, of course. There we go. I've reached the top of the virtual map, and so I'm just editing the blocks there up at the top so that we have a start and end range in memory of something to look for. And again, that data is going to have to get saved out too. So the goal for this first video is to show you how the background can be extracted and then to render that background. The goal for the next video will be to look at, say for example, how the levels are constructed, how the static screens work and so on and so forth. But this video is going to be long enough already just looking at how to extract the map data and the characters and the blocks. So there we go. File name, map, top to bottom, or top bottom, indicating that I have changed the top and the bottom of the virtual map. The next one would be changing the block colors. So each 5x5 block allows you to have an individual color, and you can have multiple characters. We can have the same character used in different blocks and have it shown with different colors. So we need to know where the colors are stored for each block, of course. If you edit the colors of the block, the two multicolors and the background color stay the same, but there is a fourth block color, basically, of course, which corresponds to the character color. So we need to know where these block colors are stored. So we'll just add a suitable file name for that piece of changed data so that we can look back and do a binary difference and to locate that data too. So if we have a look at the directory, we now have these files. Let's sort them by the date modified so that we could actually see which one was saved first and then subsequently the other ones. So we have the base one down at the bottom, then we have the characters changed, the colors changed, the blocks changed, the map top and bottom changed, and then the block colors themselves changed. Okay, so that was the order in which we made those changes. So that's what we need to look at now in terms of a binary difference. The first one is changing the characters. So we're looking for at least 8 times 256, which is 2048 bytes long. We're looking for a range in memory of that amount of data being changed. So these small 1 byte differences, and we can see here a message saying press fire to commence super death. I don't know what that is, but anyway, these single byte differences are inconsequential. They're not related to the character set changes. We're looking for much more data being changed than just 1 byte here, 1 byte there in individual places. So we can ignore those. Maybe it's some state of what menu was last used, for example, the last position of the editor cursor or something like that. That data looks a little bit interesting, but I think it's editor-related data because it's extremely close to those editor-related text prompts. Maybe it's what was behind a particular window, or maybe it was a temporary block that was being edited or for the block copy purposes. This data, however, looks interesting. The changed data starts at EF1C, and it is practically at the end of the memory for this particular data file. The start of the data being EF1C is interesting because I know that in these P00 files that are saved out from the emulator, that the first 1C bytes from 0 to 1B basically is actually the file header plus the start load address, which is what's saved out by the Commodore 64. So this tells me that this is data which is aligned to a 256 byte boundary in the Commodore 64's memory, assuming that they start from that aligned boundary. And I can see actually in the differences preview on the left that there's also some changed data practically right down at the end of the file. So I'm pretty sure that this is the character set data, and it starts at EF1C in this save all data file. So let's update the documentation with what has been discovered. So the characters start at EF1C offset within the file. Thinking about it, I need to change these offsets to something where I think is consistently within the Commodore 64's memory space. So that, say for example, if somebody just saves out the whole of memory, then it would be a lot easier to translate that back to what our Commodore 64 address is. So we'll need to find out the start address of this save all data file and map it back to the Commodore 64's address space. So we'll need to remove the header offset, for example, and then add an offset from wherever the Commodore 64 was saving from. But we can see that these last 8 bytes were changed, and this corresponds to the data that is in the Commodore 64's character set that was changed as well, of course. So these P00 files have all of this data at the beginning, and then the 42 and the 00 is actually a weird, wrong start address that was saved out by the Commodore 64. I noticed that back in the day, is that if you try and load these files in, so for example load the file 8, 1 or 1, then it would try and load all the way back at the beginning of memory, and that was obviously the wrong address. Because it wouldn't be saving 0 page and stack and everything else like that. It doesn't look like it's saving 0 page and stack from the beginning of the memory. So we need to find a better way of actually synchronizing the data that we can see in the save all data file with data that is in the Commodore 64's memory. We can do that in a couple of different ways. We can look for specific markers, or we can set a specific marker in the memory in the Commodore 64 and then save all of the data again, and then have a look at that. So I think what we'll do is that we'll put a very specific marker in the memory at E001 because it looks like it's blank memory, and 2, I think that it is saved here, so that's what we've done. Then save all of the data using the storage menu again, as always. Give it a suitable file name like marker so that we don't forget, and then look for that marker, and it's the first occurrence here. There it is. So the offset within the file, even though I saved it at E00 in the Commodore 64's memory, the offset in the file is actually starting at 51C. Remember, the first 1C bytes of the file is the file header plus the load and save address. And that matches up, or it needs to match up with E00 as the address there. So we need a little bit of maths. So E00 minus the observed start address in the file, which is 51C. So we take 51C and we minus off the file header first, and we have 500 in hex left. To get from 500 in hex to E00, we need to add on 900 in hex bytes. So that's the maths that we need to convert the observed file offset for particular data, and then convert it back to the memory address. So if we take the observed file data offset, and then do that maths, subtract 1C, add 900 in hex, we get F800, which makes sense. Character sets are on 2 kilobyte boundaries. In other words, 800 in hex byte boundaries. That's where character sets usually are, because that's where the VIC chip, the video chip, wants to look for these things. So there we go. That's the maths that we need to map from the observed file offset to the Commodore 64's real memory address. So I think it makes sense to actually document the offsets of the data as basically the addresses of data inside the Commodore 64's memory map. So let's go back to looking for file differences now. So if we have a look between the characters file now and changing the background and multicolor colors, let's look for that. difference using the same tool, because I really do like this tool. So the characters to the colors file, we're looking for 3 values being changed, basically, which I think are those bytes there at 3796. Roughly, it's not 3796, it's 37A2, A1, A0. There we go, it's 37A1 is the first byte that was changed. So we take 37A1 minus 1C plus 900 in hex gives us 4085 in hex of the first 3 bytes of the background multicolor 1 and multicolor 2 byte offsets in memory. So the first number is the file offset, and then the second number is the memory address within the Commodore 64's memory. We need to look at the block differences now, so we need to find the memory locations for the blocks. The blocks are, as we've previously seen, 5 by 5 character cells, and there are 128 blocks. Actually, it's quite a decent chunk of memory, right? Generally, I tend to use 4 by 4 character cell blocks, sometimes 3 by 3 character cells. I've seen people use 2 by 2 character cell blocks before as well. 5 by 5 character cell blocks was a little bit large, a little bit low resolution, perhaps. But it's just a design choice at the end of the day. Anyway, so this data looks quite obvious, doesn't it? I don't think that's the end of the block data. I think the end of the block data, it was actually up above, and then the start of the block data was actually above that, of course. It makes sense that the block data is contiguous all the way through memory. In other words, as one block. Doesn't make sense to split it across multiple memory ranges. There are some games that do that, however. If you remember my video from, Turbocharge. Turbocharge, I think, if I remember correctly, has a split memory arrangement for the roadside objects. There are 2 banks in memory, and in the middle of it there was some extra data or something like that. Was it Power Drift or was it Turbocharge? I think Power Drift used 1 chunk of memory, and I think Turbocharged used 2. Anyway, so we can see here, I think this is the end of the block data that was changed. So we're looking for 25 bytes, or a range of 25 bytes, and that looks kind of it, right? Does indeed. Let's just double check that. So don't forget, I changed the last block to use some character number 3s inside that last block, so I'm pretty sure that we're looking at the last block data here. That's what it looks like to me. So we'll take the last memory address range, which is what the only thing that I don't like about this tool is that it doesn't tell me how many bytes I've got selected, so you have to do the calculation manually. So 1D88 1D88 was the end of changes, and the start of the changes was 1D9B. Sorry, 1D9B minus 1D83 is 18 in hex, which is 24 in decimal, so 0 to 24, which is 25 characters. So that's the 5 by 5 block at the end located, and of course the blocks at the beginning, you would hope, are in the memory up above it. So there we go, there's the last character of the last block, 1D98, minus the start address of all of those changes here, which is 111C equals that, 3199, so 3200, divided by 25 equals 127 blocks. So I'm pretty sure at this stage, when I'm looking at this now, that that's where the block data is in memory. So let's note down those address ranges, translate that into the Commodore 64's memory, and of course that looks like a nice rounded number in hex, doesn't it, aligned to a 100 in hex, or 256 decimal bytes. Memory page indicates to me that the data that's been found is good. We then look for The map data. Scrolling through the file, we can see these patterns that have been introduced where the new data is actually showing on the left at the moment. Let's swap it over. There we go. The new data is on the right. The existing data is on the left. So all of those red bytes. So yes, remember when I was looking through, scrolling through the map, adding blocks as I was scrolling up through, and I was waggling the joystick left and right. That looks like those pieces of memory. The patterns look similar, right? I don't think that's the start of memory. It's not rounded. It's an unaligned memory address. I don't think that's the start of the map. And of course, scrolling up to the top of the file. Yes, of course, the real changes are here. Look. So the first, so block number 2 was put up at the beginning of the map data, which is going to be here. So I can do this arithmetic in my head. So the file offset is 1C. We minus off the header size, which is 1C, so we get 0 bytes. 0 offset, and then we add on, of course, 900 in hex. Of course, 0 plus 900 in hex is still 900. So that tells me that that's a much better range of memory to actually have a look at. That's a nice aligned memory address. So the eagle-eyed of you might notice that although I put block 127, which is 7F in hex, at the bottom of the map, those 7Fs appear at the beginning of the map data memory. I think the map is stored backwards, or rather bottom to top through memory, even though the blocks are stored top left to bottom right. I think the map is stored bottom left to top right, effectively, so I think it's stored reversed in the Y direction, basically. So the last bottom part of the map is actually the first part in memory, and so on and so forth. So to really validate this, let's put 8 changed blocks up at the beginning of the top of the map, right up at the top of the map. And of course, nothing has changed at the beginning of the map data. So to really validate where these map rows are being stored in memory, I've put block 0 up at the top, block 1 underneath it, which are the red blocks there, and then block 2 underneath the row of red blocks. So let's save out that as all data. Let's look for file differences there, and then we can see here where the differences are in the map data. And we can see that the map data is actually confirmed to be stored in a reverse fashion through memory. So the top of the map is actually the end of the memory block. Those 8 0 bytes there, and then immediately preceding those 8 0 bytes are 8 1 bytes for block 1, and then immediately before that are 8 2 bytes for block 2. So that confirms in my mind that the map data is stored reverse order for the Y, so bottom to top rather than top to bottom, which kind of makes sense. The game starts, generally speaking, scrolling at the bottom of the virtual map and then goes up, so it kind of makes sense to store the map reversed all the way through memory, so that if you want to shorten your virtual map, you just have to bring up or move up the end of the memory for the map rather than shuffling around all of the memory like that. Makes sense. So let's put a little note here reminding us that it is backwards rows of 8 bytes. Lastly, to find the block colors, let's have a look at the binary difference between these files. We have 128 blocks, so we're looking for a memory range of 128 bytes, I expect, and that looks like it there. So that starts at 101C. If we minus off the header of 1C bytes and add on 900, we still get a nice round memory address, which is 1900 in hex, which is great. That's the memory address in the Commodore 64's memory, basically the memory map of the SEUCK editor, shooter map construction kit editor rather. So there we go. we have all of the information that we needed to find out now to get the scrolling level map working. Basically scrolling the map from all the way from the bottom to the top. So we just need the code to be able to do that, and then we'll get something working on the screen. However, what we can do is that we can make use of the tools that we have these days, of course, to validate the information that has been discovered without needing to write any code at all. So far, we can use, say for example, CharPad to load memory from a snapshot. So here's CharPad. Now with CharPad, it's easier for CharPad to import a VSF file and then to extract things from those memory ranges rather than save out individual raw dumps of data. So I'm going to save a snapshot t.vsf into that debug1 directory. This is demo1 snapshot, so it's from the demo1 game. So let's make sure that tiles are enabled, that the coloring method is per tile, that we've got multicolor mode enabled. Let's import the Vice snapshot, and then we put these values in that we found. So F800 for the characters. The tile set. Now we know the map width is 8 tiles, but I don't remember the map height. We know the map data format is bottom to top, of course, but first of all we'll set that to be, what was it, 1A00 for the tile set, yep. And then the map starts at, what was it, 900, wasn't it? There we go, so we'll put that to be 900. We can assume that the map height is going to be something like, I don't know, 100 or something like that, so we'll put 100 tiles height in there. The map data format needs to be left, right, bottom, top, instead of left, right, top, bottom. We need to load the VSF file, of course. So let's get back that window. So where was that VSF file? There we are. We will get those values back. Recall, there we are. And there's the tile set, and then there's the map. So I think that looks okay. We'll just click OK there. We'll scroll all the way down to the bottom, and there we go. There is the start of the level. That was a good guess, wasn't it? Scrolling all the way through to this, to the tiles, to the space area of the level, to where the boss appears, and so on and so forth. So that kind of tells me that the data offsets that we've got are good without needing to write any code. So if we have a look at the code, pay close attention to the file name up there, scroller data.a. This is the address for the character sets F800. The colors are tagged as 4085. There we go. You can see there that we're adding on +1A, +2, which is +1C, and then minusing 900. We're doing the opposite of the mapping back to the file offset from the memory address. There's the blocks there at 1A00. The map data, we say that it starts at 900, and then the colors for the blocks starts at 1900. These are block colors, block data, map data, and map data end labels that you can see in that source file. Then we have the scroller single.a file, which contains the draw blocks routine. There's the 5 times table lookup there, which gives us the horizontal character position on the screen, for example. There is a block table as well, which takes a block index from 0 to 127, or the block number, and then converts that into a low and a high address for the 16-bit address in memory. The memory offsets used by this code, of course, are very, very different to the SEUCK in-game memory offsets, or the in-editor memory offsets, and that's because we're optimizing the memory layout. So all of this code, all of this memory layout is completely different. So any pokes for infinite lives or anything else like that, or collision in SEUCK will not work in this code, because the code is all new and the code has completely different memory layouts. And that's because that allows us to optimize everything. It allows us to squeeze extra data into memory, and we can do that later on in one of the later videos. But this is just a very, very simple scrolling level render. We can see how the block drawer has been optimized, which draws the blocks at the beginning of the level. But then the new block data is introduced a character line at a time in the typical way of smooth scrolling. So the draw map draws a block aligned view of the current map position. It's also used for drawing static screen portions of the game, which we'll get into in a later video. But this is just the optimized partially unrolled loop for doing the scroll with using in the index register, but also having the character rows being slightly unrolled to make the routine faster. Uses a double buffer, and there we go. There's the map data imported from the shoot 'em up construction kit, scrolling quite happily in completely new code. So we can see that the block colorization is correct as well. That can be validated by running the SEUCK version side by side, or actually running the SEUCK editor on the left, say for example, and then running that code on the right. So that's what we can do. So here on the left, I will always use the left-hand view as the original SEUCK editor view, or the SEUCK game view. So the bottom left is SEUCK, and you can tell it's SEUCK because it's the map editor, and you've got that expanded sprite with the flashing border around it. And then I will always use the right-hand view as my code, so that it's easier to compare. There's the editor on the left, and then my code on the right, scrolling up. So let's jump ahead in the map editor view. You can see that the blocks and the characters and the colorization is actually identical. So let's put these views side by side. There we go. So if I move up in the map, you can see that it all matches. The colorization for this different area here uses a different block color, so we can see it's working. And then we scroll up a bit more, smooth scrolling on the right, jumpy scrolling on the left, because it's the map editor. It just scrolls in tile jumps. There you go. The colors all match and everything looks fine, right? So I think that's a good point to leave this video here. The next videos will go into levels, probably sprite animations and stuff like that, and player animations, but we'll see how that goes. Thank you very much for watching. If you like these kind of deep technical dives into Commodore 64 retro games, and specifically reverse engineering, then please do consider liking or subscribing to this channel, and I hope to catch you around next time. Have a great day wherever you are.